Now, today I'm so excited to be hosting Hemant, Fleet Space's Chief Technology Officer, Gerrit, Fleet Space's Chief Scientific Officer, and Tim Jones, the Head of Exploration Geoscience at Fleet Space. I am a senior geophysicist and I am just hosting today, but I'm so excited about this webinar. We're going to be talking about Meteor, and Meteor is a seismic-led exploration workflow and it integrates geochemistry, geophysics, it's data-driven, and this is all to produce a single structurally informed model that's ready for drill targeting with confidence. So let's get into it. I'm stoked to talk about this again today. We did this yesterday, but let's just do this even better today. Hey, month. Oh, let me share my screen first. We need to have these slides up.
Oh, good.
Then
I'm getting ahead of myself.
just just talk through the whole thing, Michaela. No slides are needed.
We can all just look at me. It's great.
Fireside, fireside chat version.
Yeah.
But while that's coming up, hey everyone, great to have you here. What we've got lined up for you is a short description of the problem to solve. Why are we doing this? Garrett's going to tell you about the seismic underpinnings of all of this and why that's a powerful foundation. And we're going to spend most of the time hearing about the specific case study at Valeriano from Tim. And we've got one more thing at the end to entertain you. Hopefully a little bit of a surprise. Yeah, Easter egg. And hopefully plenty of time for Q&A. So as Michaela said, there's the Q&A chat function in the chat. Feel free to use that as we go to raise questions, and we'll make sure we cover as many of those as we can. So the problem to solve, I wanted to start off with what's the point of all this? What are we trying to improve? And between Fleet and HiSeis, which is now all one happy team, we've done hundreds of customer engagements with mineral exploration teams to help them advance their programs. And so we see patterns. And one of the, if you step back at the sort of the highest level, this is a way of summarizing what a common problem is, which is that you're fundamentally betting millions on targets you can't see. This is the problem that we are trying to improve upon. And the reality is that targets that you're interested in for mineral exploration are increasingly deep, increasingly undercover. They're not outcroppings anymore, not usually. In this setting, you've got geophysics on your side to help you see at depth, but you know that any one method is ambiguous on its own. There's no silver bullets in this space. The geophysics, depending on how it's done, can often have an unclear connection to geology or measured uncertainty. So a pretty common approach is overlay the different data sets, whether that's seismic velocity and resistivity, mineralogy, whatever you have, overlay them, make a manual interpretation with the best sort of judgment that you can make, and drill based on that. That's one way, but then it sometimes leaves you wondering, how could you get more insight out of each result? Each new drill hole, how can you get more out of it? There's got to be a more systematic way, a more data-driven way. So this is what leads into what we've built in Meteor, which Michaela has introduced already. But on the next slide, a pithy way of describing it is that Meteor is a seismic-led workflow for drill targeting that's fundamentally data-driven with quantified uncertainty throughout. So as an example, you're going to hear later from Tim about how we've applied this at Valeriano, but it begins with seismic surveys, ANT surveys and models, which in the case of an exploration project, that can tell your team what the seismic velocity looks like in 3D at the subsurface. That's obviously not enough. That's a first question to answer. So the more interesting question than that is, what does it actually tell me about the structure, the geology under the ground? And that is where we bring in our geological interpretation capability with awesome geologists inside a fleet collaborating with your team, translate what the model is saying about the geology and turn that into structural interpretation. But then that's, again, not really the right stopping point, right? Because that's still just based on ANT. So where Meteor goes next as a workflow is to ask, what can you learn by combining ANT with all your other data? Bring all the data that you have to the table that is not just A&T, but all the other geophysics, 3D, 2D, whatever. Also your drilling, which is your ground truth. Also your geochem. Any data that you have, bring that all together and bring it together with our ML, our machine learning targeting technology, to create one coherent model of the subsurface that answers your actual question, which is where should I drill next and why? What is the data-based, data-driven sort of logic for that target? So this is what we mean by Meteor, a seismic-led workflow for drill targeting that goes all the way to the decision that you actually need to make. The underpinning of this scientifically is seismic, though. So I'm going to hand over to Gerrit, who is going to tell us more about the seismic foundation underneath this and why that's so important.
Thanks, Hemant. Yeah, so before I get into how we specifically use seismic data in this drill targeting workflow, let's just step back for a second and think about how we've been doing exploration for the last 100 or so years. So we typically think about it as in three eras. So people like Richard Shoddy refer to it like three eras. There's the prospectors era, which is the early 1900s and before, obviously, where we relied a lot on field mapping and visible signs of mineralization at surface. Post World War II, we entered into the geophysics and geochemistry era. So we did a lot of airborne gravity and magnetic surveys, and that led to a lot of important discoveries like Olympic Dam. With geochemistry, we started looking at very small concentrations of elemental concentrations in soil and rock and drill core samples, and especially looked for these kind of pathfinder elements that indicated that we're close to some mineralization. And then from the 2000s onward, we get into what's referred to as the big data and deep exploration era. So this was kind of kick-started with a lot of leading minds started to think in terms of mineral systems. So what factors need to occur for a mineral deposit to form in what areas? What are the key contributing factors that led to that? From the early 2010s onwards, we started doing a lot of 3D electrical geophysics as well. So that was, again, because we were thinking about mineral systems and about the mappable features in the shallow crust, and also because of the advances in computational geophysics and 3D inversions, we started doing a lot of electromagnetics and induced polarization and magnetotelluric 3D inversions to try and really find these mappable features of mineral systems in the shallow crust. So you might wonder what's next in this kind of workflow. A lot of people think that AI and machine learning is the next kind of era that we're entering, and that we can build on all this data we've collected before to kind of really tease out things that the human eye misses. Like Hemant said, not just laying things on top of each other like a light table, but looking for more subtle correlations between all these variables that we're measuring. But in my view, I think before we do that, we're going to see a lot of adoption now in 3D seismic methods. And it's because 3D seismic methods are probably the geophysical methods, all things considered, that are best suited to imaging structures. And because we know that structures are such an important part of mineral systems, it's how mineralizing fluids come up to the crust. It's often also the trap where these mineralization events occur. We see that there's a huge utility in this kind of broader data ecosystem for mineral exploration. And after that, there's lots of uses for machine learning into incorporating all this data. You may wonder why seismic methods have not been used in the past very frequently for mineral exploration. For instance, in oil and gas, obviously, it's been this slide would just be 3D seismic, basically. Well, it's because there's kind of technical and practical reasons. Well, technically, the geology we operate in is much more complex than the typical passive margin basins that we look at for oil and gas. So we're not looking at like layer cake structures. We're looking at very complex, deformed, folded, and torn apart structures. The rocks are a lot older, so it's been exposed to much more geological events than we typically look at for oil and gas. And then there's also a practical application where oil and gas deposits are deeper and more valuable. So the relative cost of a 3D survey in oil and gas to drilling is much lower than in mineral exploration. But what's happened over the last, call it 15 or so years, is that we've seen two things happen. We've seen a growing body of evidence for the use of 3D active seismic in mineral exploration, spearheaded by HiSeis, of course, since about 2010. the image on the left shows a fantastic image of how we can use 3D seismic to image different parts of the mineral system. In the pink outline or isosurface we see there, we see deep intrusion here. That's the source for the heat and mineralizing fluids that come up to the crust via the red structures, which are the interpreted faults. You can see there are different aspects here that we look at. So the intrusion here is very clearly seen as a lack of a reflection due to the alteration halo that surrounds it. So it acts almost like an absorber or a diffuser of seismic energy. And the faults themselves we see as sharp reflectors. And when we look at the drilling near surface, we see that mineralization exactly occurs in these areas where we intersect these faults. So a fantastic image of how we're seeing the different parts of the mineral system imaged by active seismic. So we've seen this growing body of evidence for the utility of 3D active seismic surveys in mineral exploration. We're also seeing that the ways that we process this data has improved remarkably. So we use a lot more full waveform inversion and other methods that can tease out this very complex geology that we see more effectively than standard migration methods. And in my opinion, it makes a lot more sense actually for 3D active seismic surveys to be done in mineral exploration compared to oil and gas, because we've seen in mineral exploration, even between very finely spaced drill holes, 100 or 200 meter drill holes, the geology can change dramatically in mineral exploration setting, which is not really the case in oil and gas. At the same time, also, we've seen in the last 5 years the rise of passive seismic methods, and in particular, ambient noise tomography. So just about 10 years to the day, we conducted the first ANT survey for mineral exploration. It was
so brave.
It was brave. It was foolish. Maybe it's a better way to say it, Michaela. So we tried to use the methods that were used in crustal seismology and apply it on a different scale. What we found very quickly is that the noise conditions are dramatically different. The noise generated by human activity is a lot more erratic and uncontrolled compared to the stable wave field we get from the ocean interacting with the crust on broader scale. But what we've seen over the last 5 years is particularly due to Fleet's computational geophysics and seismology team, the R&D efforts that they've been doing, is how these methods have improved. So compared to 4 years ago when we started this journey at Fleet, the models we're getting now is remarkably better. It's chalk and cheese, actually.
That's an understatement for sure.
Yeah, Michaela, you're lucky you joined us actually after things got a lot better, right? So you joined us like a year ago when we've made a lot of the improvements already. But the first few surveys, we were really kind of still building the plane as we were flying it. And right now we have a workflow that's, I can confidently say, the best in the world and by some margin, and we're producing incredible results. The result you're seeing at the bottom there is a porphyry copper deposit in Pakistan called Reko Diq, and we see these granodiorite intrusions, again, an important part in the mineral system of why this deposit forms and how. So the way that we incorporate seismic data typically, like Hemant said, is obviously qualitatively, we do that by interpretation. So in the top left panel, you see ANT data here on quite a regional scale, jointly interpreted with magnetotellurics in Saudi Arabia. It's a paper from Anthony and Michaela. I think you're involved in this paper too. We see great correlations between these two data sets, and we see the accompanying structural and geological interpretation from that. So by really closely examining these data sets and all the data we have and considering the tectonic setting and the tectonic evolution of the area, then we come up with a very detailed geological interpretation of what's happening, and that informs our downstream decisions about where we want to explore and what actions we want to take next. A more mathematical way of how we combine these data sets, particularly seismic and meteorologics, is in a joint conversion. So this image here shows a synthetic case study from a paper from a couple of years ago, where the true model that Michaela is highlighting at the top there consists of a conductor in the near surface and a conductive basement, typical of what we see in many places, parts of the world, where we have, say, graphites in the cover sequence and a conductive basement, crystalline basement that we're looking for. And in this case, you see that if you just invert the magnetotelluric data by itself, it looks like these conductors are connected. So you can see that this looks like very appealing from a explorer's perspective. This looks like it's a shallow conductor that's been fed from deep, but in reality, it's just non-uniqueness and uncertainty in the inverse problem.
It's like a finger of God, doesn't it?
It does, yeah. That's maybe a topic for another day, but yeah, that's we are thinking about, what does that mean for those types of results where we see these deep conductors and are they real or not?
Mm.
So if we then invert that with the seismic data to do a joint inversion, in this case with a cross-gradient approach, you can see the seismic data that Michaela highlights there indicates that there's no connection between these two because there's differences in physical properties. You can see the conductor in the near surface is slow, which is indicated by red, and the basement is fast. So that gives us a really good way to decouple these two physical properties. So they're structurally related, but they have different physical properties, which we see often in magnetotellurics and seismic. So when we do the joint inversion, then we see these are no longer connected and gives us a much clearer view of the subsurface. The other two ways that we combine these data sets is in an unsupervised machine learning approach. The top right image shows work by Simon Carter at the Vulcan IOCG deposit a few years ago, where we collected ANT and MT and other data as part of a ADI grant. And we see here the 8 clusters, which basically divide space into regions that have similar physical properties. This is often called the pseudo-lithology map or pseudo-lithology volume. And here we're just looking at rocks that have similar physical properties. This is a very effective way for us to interpret data that's from multiple sources, because it gives us the kind of geologist an easier view of where the rocks are a similar physical property. And it's also very effective in areas where we don't have much drilling. In areas where we have a lot more drilling, there are much more effective ways how we can combine this multi-physics data and the drilling we have available. And this leads us to a way how we can combine the seismic data along with all the other data in a drill targeting framework. So what my colleague Tim will show next is how we use the seismic data and all the other data we have, train it on the drilling that we have available, and then inform what our next action should be. Tim, up to you.
Great. Thanks for that, Gerrit. A great introduction to kind of the why behind different components of Meteor. What I'm going to show you now is how we've applied this for a real project here, Valeriano, which is a copper porphyry in Chile. It's quite a mature project, so the story I'm going to tell is not a discovery story. Fleet came long after Valeriano had been discovered, but here we're answering the question of ATEX. What can our data tell us about where to go next? So they're at the stage where it's already got a resource estimation in the billions of tons. It's been through 6 phases of drilling. And right now, what we want to make sure is that every drill hole counts, that we're kind of getting into the nuances here away from potentially just the main deposit and finding extensions to that. So Michaela, if you go to the next slide, yeah. As Michaela pointed out at the top, Meteor is a data-driven workflow for drill targeting that's based on seismic as its kind of foundation. What this meant for Valeriano is that we use ambient noise tomography to constrain the bulk physical properties of the hydrothermal system. We use the MT data that they'd already collected, we remodel it, and we use that to delineate some of the minor phases, really important for understanding sulfide connectivity and the presence of fluids. To kind of tie that to the geology, we introduce COMET, which is a framework for understanding mineralogy from geochemical data. And then we produce targets by integrating it all in our machine learning framework and quantify confidence. On the next slide, the thing that you see here is the MT data that was already existing before we came along. Now, the background is colored by electrical resistivity. And the S sort of shape here is a contour that just outlines the main conductive feature that we see beneath the subsurface here. You can see that the model itself is not particularly complicated. It's pretty much defined by that single conductor. And so if you're looking to run the next hole in a way that's going to kind of target the highest grade possible, it's very tricky to do based on a very simple picture like this, that really any single physics is gonna give us something like this. So the downhole values we see are copper percentage normalized to the maximum values here at Valeriano. And what the MT model does nicely is it really highlights where we're seeing kind of the most copper productive part, or at least the center. We see some really high values at depth down to 2 kilometers beyond where that main conductive feature is. And one reason for really leaning on MT here as an electrical method, we might typically think of IP for a porphyry deposit, but most of what is interesting here is below about 500 meters. So the sensitivity for IP is highly limited in a sort of whole system view like this. If you go to the next slide, this is where we introduce our seismic data set. So we've highlighted two different features here that we've extracted from the seismic data. And the first thing you'll notice is a completely different view of the deposit than we get from MT. Maybe initially on seeing that, people might think, well, okay, what am I supposed to trust here? These pictures are so different. But the reason we often combine seismic methods with an electrical method like MT, and in particular this combination of ANT and MT, is because they're anti-correlated. So we're really maximizing the amount of unique information from just these two data sets by selecting things that are sensitive to very different parts of the Earth or very different physical properties. So by contrast, ANT is much more sensitive to the major phases, the changes in lithology and rock competency. On the left-hand side, you can see the network of faults that we've mapped using ANT. Now, because faults are essentially damage zones, areas and planes of broken, in this case, altered rock, the competency of that rock goes down, and so seismic velocity also dips. So these faults tend to show up as low velocity zones. On the right-hand side, we're showing something slightly different. Now, the major contrast you see is between the shallow, low velocities at the surface and those much higher velocities at the base. Those higher velocities relate to the really competent, strong potassic core, the intrusive bodies that are part of the porphyry system. What we've outlined with that purple contour are kind of intermediary values where we see that competent rock being altered, where minerals are replaced by weaker ones like sericite and clays, and this also decreases the seismic velocity. So these two really important parts of the system, alteration on one hand and the fault network on the other, are things that we find are really helpful for improving targeting in these kinds of systems. On the next slide, we're introducing Comet now. So for a variety of reasons, we want to understand mineralogy. As a geophysicist, one of the reasons I love to understand mineralogy is that I don't sort of care how fancy or complicated the rocks themselves are. What I care about are how they relate to physical properties. And mineralogy gives us some indication of the petrophysics, which is what the geophysics is mapping. And so I can more directly relate those geophysical signatures to geology if we have that understanding of mineralogy. Now, it's a thermodynamic model, so it relies on making some calculations and assumptions that link your assay data, the kind of standard ICP assay data that most people are already collecting. And where it sort of sits is that if you're typically trying to understand mineralogy, you can do at one end, just looking at core and visually inspecting and logging the minerals present. Or you can do something far more robust and accurate, and directly analyze the mineralogy with something like scanning electron microprobe. Comet really sits in between those, being a model that links real measurements, but in this case of geochemistry, to that mineralogical system. What we highlight are these two ratios. We can get much more out of it, but just to kind of give a quick picture of the porphyry system here. There's this sulfide ratio, which we've identified maps nicely onto the kind of copper center. Actually, if you click Comet copper down the bottom there, Michaela, you'll see those are the downhole copper values calculated from Comet. The outer shell is a silica ratio that we use to map the alteration zone. So these two very important features of the system can really be rapidly understood and mapped using Comet. If you have your standard ICP assay data and a reasonable amount of drilling. And what that geochemistry is telling us is that the system is indicating it's still quite open at depth, even compared to what we see in that background image showing the conductivity high that MT is relating to. On the next slide.
Tim, you gotta say, why do we call it Comet? Because we get a little funny with the space names.
Oh, yes. Okay, yeah. Actually, that is a very important point, because we developed this tool in conjunction with Scott Halley, and so it's Halley's Comet. So I guess the name was like something kind of cute that also helped us link to our space background, but it's really Scott. So we partner with Scott to do all this and to build this, and yeah, he's the one with the very deep domain knowledge here and makes it all happen.
Happy coincidence that it's Scott Halley's Comet.
One thing that we might do before introducing any kind of more sophisticated data analysis is just try to reduce the search volume using the information that I've just talked about, that combination of geophysics and geochemistry. If we highlight the ISO surface on the very left purple image for ANT that we think is highlighting that sort of strong, competent, intrusive package, we get a fairly wide area. If we then highlight in the middle the oh no, the click reload. Okay, we've got to go back to it.
You keep talking, it's loading.
With MT, what we highlight is that that sulfide network, and in particular, because of its abundance, we're talking about pyrite here, not copper directly. And so the combination of these two things, when we compare it to the mineralogical model we get from Comet, looks like we're zoning in on when we look at the overlap of these two things, which is the right-hand side, is the kind of potassic to phyllic transition zone in terms of mineralogy. And so we're able to rapidly reduce the search area to 70% of the survey space just by linking and looking for the mineralogical vectors for copper that point to the most productive part of the system. So this kind of search-based reduction is something that you can do at a much earlier stage. now that we have information about what these geophysical signatures relate to, we can really link it to the mineralogical part of the system that we're interested in. But we're still relying on sort of manually derived isosurfaces and cutoffs here. What we want to do is ask, how can we allow the data to do this for us? So this is where our machine learning targeting tool comes in. We use a supervised machine learning approach, which simply means we feed the model a large amount of data where we already know the answer. We already know what the downhole copper values are, copper grade is, and we know what the geophysical signature is, or at least we've inferred that signature from the data that we've collected. And then the model learns the relationship between the two. So we understand that relationship at the holes very well. That's our ground truth. And what we want to do is propagate that out and look away from the holes. So here we combine the 3D, ANT, and MT that I've already talked about. We include other 2D native data sets, potential field data, geologically mapped faults, and again, that drilling data. What we get out is a 3D grade prediction across the whole 3D volume, a quantified uncertainty, and also an assessment of what is driving the prediction so that we can actually explain the targets that this ML model produces. If you go to the next one, Michaela, before I show you the model, just a quick note on some kind of validation exercise that we do. We want to ask, are we just fitting data, or are we actually able to genuinely predict away from those drill holes? The line here is showing where all the data would lie if we were making a perfect prediction. We don't make perfect predictions. And you can see that for the kind of low to moderate end, we're doing a very good job. The points are clustered on that line. Where we have outliers is really where we have the least amount of data, which is where we have these more extreme outliers of grade out to the right there. Yeah, so a few sort of statistical values here. We get a Spearman correlation of 0.83 and a median error of 0.048% on a cutoff of 0.35% copper. And that copper is just unique to the project in terms of what is helpful for ATEX today. If you could go to the next one, Michaela. So this is what I was talking about in terms of the explainability, being able to kind of account for what is contributing to the predictive value of the ML model. So what we see is that the most important data sets are ANT, MT, and MAG. So ANT being at the top sort of validates our underlying hypothesis that a material property that maps the fault network and alteration is going to help with targeting, not just at the interpretive stage, but at the sort of data-driven, what can we really predict from the data stage. MT is next, and MAG comes in third. Clearly, there's no single data set that we can use here to really predict copper grade. It's more about, and in particular here, how ANT and MT interact and how the copper grade actually co-varies with those two physical properties that we're measuring there. So a nice guide to what we're able to explain in the model, but also something that we can use to ask what technique do we want to further invest in. Next slide, Michaela. This is really the output that you start interacting with from Meteor once you get the the everything through the pipeline is this model that tells us here 3D grade predictions above 0.35%. Again, a cutoff that can change depending on what your goals are. The coloring is not grade. The coloring is uncertainty. And we find that uncertainty is not just a kind of nice to have. It makes up the prediction itself. If you really want to make a decision when you get these predictive values, you need to know the level of confidence that is coming out of the model. And you don't always see this in machine learning outputs. It's sort of more expensive to compute than the main predictions. So it's not easy to do, but just like any sort of everyday prediction, you don't just want to know that it's going to rain tomorrow. You want to know if the rain is going to have a chance of 10%, 30%, 90%. And that will change your actions. That will change whether or not you take an umbrella, whether you walk to work, whether you take a car. And similarly, in a targeting sense, you can invest heavily where you have high confidence. You can put a smaller amount into riskier bets that have a big upside. These are all really important for decision making and a core part of what we output for Meteor. If you just look here at the Valeriano case, Michaela, maybe if you kind of spin it around a bit here, you can see that the most kind of certain values are right where you'd expect them, all around the jewel hole. But there are some fairly confident targets off to the east too, and a nice extension off to the west. So I think the sort of target one that we have labeled there is that extension out to the west, and the target two further away from drilling out to the east. On the next slide, I'm going to go through a little bit more just detailed validation. So we pulled out a number of the deeper holes here because we want to know how well do the predictions hold up at 2 kilometers depth, for instance. We've chosen techniques, MT and ANT, that should have sensitivity at those depths. So we want to know how well are we doing at predicting grade right down there. And actually, something that I should mention, maybe even before this, is that we're not predicting at the same resolution as the assay data, and we're not comparing against assay data at 2-meter resolution. We average the assay data over about 35-meter blocks, so something that is comparable to the resolution of our input data. Michaela, on the next slide. Sorry, these white holes, these white lines here are the holes, the deep holes I'm going to show you. So the chart on the right-hand side shows copper percentage versus depth, and we've got the predicted and the measured values. The measured values have 2 lines representing them. One is the 2-meter interval prediction, which obviously has a lot more variability. And the other is in this case, it's a 25-meter moving average. And so you can see that 25-meter moving average is flatter, it shows less variation. But key is to look at the predicted value against that 25-meter moving average. So we provide the 75th and 25th percentile predictions out of the model as a function of depth. And you can see that we're doing a really nice job of bracketing that true value. So the true value sits between the 70 and the 25% prediction, even when we get to higher values in the B2B breccia zone. And I think what's really impressive is that correlation holds up even down at 1,500 meters, right down to 2 kilometers depth. And this is why both ANT and MT are particularly important, because they have that depth penetration. Whereas you might think that you're getting a lot out of your mag data, and you probably are, but it really depends on the purpose. In this case, when you want to predict something as fine as copper grade down at 2 kilometers, we need something with better depth sensitivity. Hey,
Yeah,
Mans, did
no,
you unmute?
Tim,
Okay.
yeah, I was just going to add to what you're saying, Tim, that what you're pointing out there in the light gray line, right? That's the true
Mm,
copper grade at the 2 meter intervals, or that like the actual measured resolution,
yes.
right? And so it's like it's really cleanly illustrating what you said before about there's no magic here. We're not claiming to predict the 1 meter resolution or the 2 meter resolution drilling, and you can see that in the
Mm,
curves. But the
yeah.
thing that is comparable is the 25-meter moving average thing. So
Yeah.
you know, for what you said, it's going to tell me if I should bring my umbrella or my drill rig tomorrow.
Mm, yes.
Always bring the drill rig.
Great. So just two more examples of this. And again, the kind of accuracy and the ability to capture even high grade at the sort of most important depth intervals for this deposit style. And how you can use this is, you're planning a hole, you've got the targeting model, and you can ask, okay, what would the intercept look like along this planned hole based on what the model is expecting. And then you can feed that in, update, calibrate the model, and improve for every subsequent hole. Great. Next slide, Michaela. So one sort of theme that is important here is that to get good predictions, we need to have excellent inputs. And so we want to collect really high quality data, whatever it is. One way we sort of quality control data here at Fleet is to have real time. Now, unlike the broken real time window that you're seeing here, the satellite transmitted data allows us to see both MT and ANT data coming in um, as we're collecting, and we can make survey adjustment to that. We can extend the recording period. We can change the geometry of the layout. We can change where the remote reference station is located. We can make all these adjustments to ensure the quality of the data is going to be sound for the really kind of detailed, nuanced predictions that we're attempting to make here. Thanks, Michaela. If we could go to the next slide. To sum up, that is Meteor applied to a case study at Valeriano in Chile. It is a seismic-led workflow for drill targeting. It integrates all your data. It ties it together with what we believe is a foundational seismic data set. And it gives you targeting at the end to really answer that question, where should the drill rig go next? That's it for me. Thanks, Michaela.
That was awesome. Yeah, some of you may have seen some of these slides before, the ATEX case study, but hopefully you got a little bit more out of Tim's explanation of the workflow today. And we actually do have one more thing. Hemant?
Oh yeah. So one more thing. I we've got something fun to show you, which is if we click forward one more. You've heard from Gerrit and from Tim about how powerful the seismic foundation is, and Tim spoke so clearly, thank you, Tim, explaining how the ANT and the MT go together and what you get out of the combination of them. You also saw Gerrit in the beginning, you spoke about the joint inversion, that academic paper, you et al., from showing how you could, in an academic sense, jointly invert these. But wouldn't it be cool if we could have this as a part of our projects? I think that would be kind of cool. So this is the thing we wanted to show you, is in the next slide, our team of insanely talented computational geophysicists and software engineers has been hard at work building this as a functionality that we can add to Meteor. So I'm going to show you how it works very briefly in a synthetic example. Here on the left is like a synthetic geology, simulating a contact at depth with something interesting in the basement that we want to image. On the top row, that's seismic velocity and imaging with ANT. On the bottom row, that's resistivity, sorry, and imaging with magnetotellurics. And you can see that in our single physics, basically one shot or by itself ANT model and by itself MT model, we don't, we get an answer, but there's
Fuzzy
obvious gap,
margins.
fuzzy margins, and with an obvious gap to the truth. So the cool reveal is in the next click. We're excited to show you this for the first time. This is our joint inversion workflow applied to that data. And you can see that what happens is that when you apply this joint inversion, which is the ANT and the MT models talking to each other, informing each other's inversions, the joint inversion of ANT on the top gets closer to the truth. You can see visually it's closer to the truth. That anomaly is more where it's supposed to be, and also the value of the anomaly magnitude is closer to the right. And similar sort of statement about the MT below is that it's gotten closer to the truth in magnitude and positioning. So this is something that we think will be a really powerful add to the workflow of Meteor. It fits in nicely, and we're announcing today that this is a beta functionality in Meteor, meaning we're ready to go do this with customers. So if to a select group of initial customers. So if this is something that you're interested in having as a part of Meteor, if you click to the next one, Michaela, this is now part of the offering that when we do data integration, joint inversion will be part of it. Whenever there's ANT and MT, we can apply this joint inversion and add an even more insightful and influential data layer into this process. So there's one more thing.
Just one little thing. No big deal.
And,
Awesome. Thank you so much, Hemant. I'm really excited about the joint inversion that we're developing, particularly because, yeah, I do think MT and ANT specifically, these are just so compatible in so many ways, not just with the complementary physics that we can sort of infer in 3D, but also just with, deployment. They're passive, they're scalable, they can cover the same kind of small package or giant areas that we've been covering in the Kingdom of Saudi Arabia. So yeah, I think this is the new Grav Mag, like for decades now, explorers have gone out with airborne gravity and mag surveys to basically create their geological maps, right? I think this is the next step. It's 3D. Yeah, this is the way
Such a
forward.
great point. I love that.
You
Thanks,
heard it
Michaela.
here first, folks. Let's see. Maybe that
That concludes the webinar. Just a few housekeeping things, I guess. We've got a few questions, but please jump into the Q&A panel, ask us questions. We would love to address anything that you want to know about Meteor, and anything we don't get to. If you upvote the questions, we know which ones you want answered, and we can get around by email and answer those for you. We do have two in the Q&A panel right now. So the first one here is, for my understanding, are you guys filtering the good MT and ANT values and making a volume out of the union of those two? So I guess this is the, that slide
The
with 77%
search-based reduction.
Yeah, Tim, I'll let you
Yeah,
first.
I mean, I guess the short answer is yes, where good means corresponding to the correct petrophysical values that map onto the mineralogy we're interested in. So
I
yes,
think it's two important points there is I think it's worth mentioning that doesn't get carried through to the rest of the targeting framework. So there's nothing else carried forward there.
correct.
The second important point is that the way that becomes really effective is if you can resolve those physical properties very well. And what we saw in both the single physics methods in the synthetic case is that we actually underestimate the physical property difference in those anomalies, because in the single physics methods, we get much closer to the truth if we do a joint inversion. So those anomalies become sharper and they get closer to the real values. So if you ever want to do this kind of petrophysically guided clustering, I think the joint inversion is crucial so we get closer to the real absolute values of what the physical properties of the rocks are.
Something I think I've been thinking about would be an interesting exercise is doing that same feature extraction but on the joint inversion models and then running that through again. I think that would be an interesting addition. We've got another question here. So what was the size, spacing and cost of the ANT survey required to generate the ANT model for Valeriano? So don't know what we can share about
So
that.
I can share the first two, which is that the spacing is about 400 meters that we used. We used 200 stations. That area, 32 squared kilometers. Yeah. Yeah, the cost part, we'll talk to you later about that one.
Yeah, take that one offline.
But maybe like a rule of thumb, it's probably quite comparable to the MT data, I imagine. So
yeah,
just as a rough guide.
Exactly. Okay, so we have one more question. So why not use deep IP data, much deeper than 500 meters? So I'm guessing this is probably referring to a kind of Ivanhoe electric type system. Yeah. Anyone want to try and tackle that one?
You seem
I
like
can try.
you seem like you're ready, Michaela.
I guess we don't have the data available at this particular case, but if we did, if the client had that data and we're willing to include that in the media workflow, then absolutely we can do that. Yeah, that's the easy short answer, I guess. It wasn't available at this site. It was regular IP data, so it was not suitable for including in this workflow. But absolutely, if you had something deeper or that was suitable, we could include it for sure.
And I think, Michaela, the IP data here lost meaningful resolution or was kind of uninterpretable below 200 or 300 meters. So what was the kind of max depth?
Well, I guess, but for this particular case, like Tim pointed out, a lot of the interesting stuff only really starts at about 500, 600 meters below surface. So yeah, you're really limiting your depth of investigation with IP, DCIP data, around sort of that, I would say maximum 700 meters, but yeah, so that's why at this particular case we didn't include it. But for other cases, maybe you've got an epithermal or something closer to surface or something in the color sequence that you're interested in, then yeah, it would be completely logic to include the IP data. That is all the questions we have today. We have 4 minutes left, so we can basically just give 4 minutes back to all of our lovely guests. Thank you all so much for your parts in the presentation, and thank you all for attending today. It's been so fun. We hope you got a lot out of this. And if you have ANT data or MT data and you want the other or you want both, reach out to us. We'd love to apply Meteor to your project. Thank you, everybody.
Bye, everyone.
Thanks a lot.
Bye, everyone.